Okay, we're going to start a section on Chapter 4. This is on microscopy. You're going to see a few of the different types of microscopy that I'm going to mention here. Want to take you over to this website. This is called Molecular Expressions, and it is far and away the best tutorial on anything to do with the microscope. Everything from diaphragms and how you use them to pictures of old microscopes to physics behind microscopy to a really great gallery. There's a photo gallery if you look up at the top of this list on the left, and down at the bottom is a movie gallery that's got some wonderful videos of bacteria, protozoa, and algae, real-time videos, short videos. It's just a phenomenal website. Okay, so let's go back here. Alright, so this is a kind of a compilation of stuff in this chapter. Mainly microscopy, some staining, and a little bit on classification. Okay, so first we need to talk about microscopy and some important features. You're used to looking at things in a microscope. You're used to looking at cheek cells, muscle cells. Maybe if you've had general biology, you've seen plants and all sorts of things in a microscope. And many of them are very large. So you've probably used your 4x, which is called a scanning lens. You've used a 10x, low power. You've used a 40x, high power. You may or may not have used 100x, which is the oil immersion, really high power lens. That's the one we're mainly going to be using in this course. Now, the problem in this course is going to be that we're looking at much smaller things than you've ever looked at, probably, in a microscope. And bacteria have no color. There are some protozoa that have color. Plants have a green color. You're used to staining already because somewhere along the way you took a sample of cheek cells from inside your mouth and stained them probably with methylene blue, and you could see the cells because the blue cells stand out against a white background. So that's one trick. We use that, of course, most of the time in microbiology. We stain our bacteria. Otherwise, they're going to be clear. The other thing you can do is change the type of microscopy that you're using. You're all familiar with what is called bright field microscopy. Your objects are darker or they're stained against a white background. We, of course, use that most of the time in this course. But we have dark field and phase contrast that we can use, and those types of microscopy very often not only look much more interesting, but they highlight an object in a way that a bright field microscopy does not. So the two ways to increase contrast of clear small objects: staining and change the type of microscopy you're using. Okay, the other thing you need to understand about is light. What is used to illuminate your objects. After all, these are called light microscopes. Now, you're looking at the electromagnetic spectrum, and it's a series of wavelengths of different sizes. Look at the wavelengths down here at the bottom. Okay, so down at the, look, right there's the scale, and you're looking at the length of television waves, a meter long wavelengths you see at the far right at the bottom. Whereas over here at this end, where you've got what is called ionizing radiation, this is ionizing radiation, X-rays, and gamma rays, ionizing. They are extremely short. You see those down here. Now, I want to point out right here in the middle, this is the visible light spectrum. So when you look at a lamp or you're looking up at the ceiling here and you see what appears to be white light, what you're seeing is a compilation of this whole area of the spectrum, which runs from 300 nanometers up to 750 nanometers. These are the colors of the rainbow of quartz of a spectrum. You know them probably as red, as Roy G. Biv. You learn those in grammar school. Red, orange, yellow, green, blue, indigo, violet. So going from right to left, you see those colors. Well, it turns out that human eyes see this area the best in green. Remember those numbers between 500 and 550. Now I want to point out a couple of things on this scale because it's going to come up later. Notice UV. We're not going to talk about it right now, but we will after we get through about 3 other types of microscopes. Okay, but for right now, think about visible light, all right? So the lamp that's in your microscope is a compilation of all these wavelengths. Okay. So, another thing to think about is magnification. I've already told you there are 4 objectives that you can have on a microscope that you're probably familiar with. 4, 10, 40, and you may or may not have seen 100. Those are the 4 usual ones. These objective lenses are made of glass, finely ground, expensive. Their job is to make your object larger. That is called magnification. And the little object, you're looking at a color-enhanced electron micrograph of a dust mite over on the right. And obviously he's very small, so if you wanted to see more, you'd make him bigger. And when you magnify, now you can really see a lot of cool detail like hairs on his legs and little purple, I don't know, dust particles or whatever on his back and so on that you couldn't see in the little one. Now there is a problem with glass lenses, and that is that when light rays go from air through glass, the light rays bend, or when they go from glass through into air again, the light rays bend. And that bending of light rays can be a problem. There's no way around it. You're going to have bending of light rays. But that bending is called refraction. We're going to talk more about that coming up. All right. So, look at the picture down here at the bottom. Let's start there. You're looking at, it doesn't even matter what the magnification is or what we're even looking at, but look on the left over here and you'll see some blurry objects. They're very close together. Some of them you can see individually, like this one looks very different from that one. You can see it's different from that one. But down in here, you can't really tell what you're looking at, if it's one object or 4 or 5 or whatever. Well, look at the picture over on the right, and you see much more detailed. This is not simply focusing. This is a difference in the resolving power of the lens. So now you see much more detail. You can actually count every little object that you see there. So I wanted to use this to demonstrate resolution. Resolution of a microscope lens is the ability of the lens to distinguish very close and or very small objects. So back down on that picture at the bottom left, the resolution on the microscope on the right is better than the one on the left. Again, distinguish close objects or objects that are very small as different from each other. Being able to distinguish close and small objects as separate. All right, there is a formula that's used to give an idea of resolution. It's called resolving power of the lens. It is a distance value and it's given in microns. And there's the formula that you see. And you're not going to have to do mathematical problems, but you need to understand this formula. It has a constant value right there. It uses wavelength of light. Remember I said that the best area for our eyes for picking up wavelengths is the green area? Okay, so let's use 550. And then you divide that number by that you multiply by the numerical aperture of the objective lens. Now, notice over here. Okay, so we need to talk about numerical aperture. It's a quality of the lens. It's based on how finely ground the quality of the lens is. Has to do with the light aperture, the cone of light going through the lens. So, on your microscope you see there's a objective lens right there, and the first number, 10, is magnification, and the second number behind it is 0.25. That's numerical aperture. This happens to be a 10x lens right there. Now if we were looking at something on this scope and switched to 40x, look what happens. Your magnification goes up, so your object will be bigger. But remember, that's magnification. You can magnify something big, but it could be blurry, no matter how much you magnify it. So a good microscope has both magnifying qualities and good resolution qualities. Now look at your numerical aperture. It's 0.65. It's a higher number, larger number. Well, note that if you put this 0.65 into this part of the formula, the larger this denominator is, the smaller the value that you get over here on the left. And smaller is better, because remember, that number is distance in microns, telling you how close your objects can be, and you can still see them distinctly, or how small your objects can be, and you can still see them distinctly. So you want as small a resolving power, a distance between your objects, as possible for the microscope to be able to delineate, because you can see much smaller objects. Now if you go up to the 100x, look at that. 1.25. If you take that number and you stick it over here into numerical aperture, that even gets you a smaller resolving power. So the smaller the resolving power, the better able you are to see close objects as distinct from each other, or small objects as distinct from each other. Now on our microscopes up in lab, for most regular bright field microscopes, of course you're going to get your best resolution using a 100x, and the resolution on 100x is 0.2 microns. Meaning that if your objects are at least 0.2 microns size, or the distance between them is greater than 0.2, more than 0.2 distance between them, you will see these two objects, this guy and this guy, as separate. If the resolving power was bigger on the microscope, like 0.5, in other words, it's not as small. And remember, the distance between these two objects is 0.2, but the lowest resolving power on the scope that you're using is 0.5, they will look like one blurred object. You will not be able to identify them as two. So you can see why the small value is what you want. Okay. So we've talked about numerical aperture. We've talked about wavelength of light, talked about the objective lenses. Okay, immersion oil. Look down here at this picture. Your light rays are coming from the bottom. You can see it as yellow. So the light rays, there's a lamp down there. Light rays are going through air. There's a hole in your stage. Here's the stage right here. There's an opening there. Light rays go through. Now, there's your glass lens right there. So the light rays are going to go through air, into glass, and back out into air again. And then they hit the lens. There's a lens right there. So the light rays are going air, glass, air, on their way to go into this lens. And every time they pass from one medium to another, they bend. So if you look at these little yellow arrows, tiny little arrows, you see the light rays bending. Well, this is refraction. Now, if you were looking at an object on 4x, which is you're scanning really low power, or you're looking at something on 10x, which is low power, or you're looking at something on high power, 40x, you got way more light usually than you need. In fact, you usually have to cut down use your diaphragm on your light. Otherwise, it's like going out into bright light from a theater during the daytime. Now, when you're on 100x, you need way more light. Because some of these light rays, remember, are not going to end up in the objective lens. They're going to be lost. But if you have way more light than you need, you don't care if you're losing a bunch of light. But you do care if you're losing a bunch of light on 100x. So notice that there is something on the right-hand diagram you don't see on the left. There is a glob of oil. Okay, so remember the light rays are coming through air. They hit the glass right there of the microscope slide. You can see them bending a little bit. But then the light rays go from glass into oil, but you don't get any more bending. Look at the interface right there between the glass and the oil. It turns out that the refractive index, that is the value that tells you how much bending of light rays this medium has, the refractive index of glass and oil is almost the same. So when you shine light rays through glass and there's oil on the other side of it, the light rays stay on a straight path. So the light rays are going air, through glass, through oil, and into the glass of the lens. So in other words, you capture way more light rays here. And you need that on 100x. Okay. Alright, so here are the light microscopes that we're going to be talking about. It would be great to have time to go into the history, the development of the microscopes, but I just want to show you what they originally looked like. I'm trying to show you all different kinds here. This one up towards the top in black and white is, latter 1600s, like 1680s. The one at the bottom in the middle in kind of a brownish tan is probably 1730s and 40s, and of course there's your microscope on the right, and I don't know what the date is of the one in the drawing. Okay, so let me take you over to, gotta find it. Here we go. Okay, over at Molecular Expressions, which I've already taken you through, there's a really great thing. If you look over on the left, there's a choice that says Microscopy Museum. That's where I am. And there are some phenomenal pictures here. You can look at the microscopes of the 16th and 17th centuries, 18th, and so on. But I want to take you over here to the 16th century, to the first one. Not that one, that's actually 1680s. But I want to take you down to, back to the 1500s. This is latter 1500s. It doesn't even look like a microscope. It looks more like a telescope, really. And it really didn't do a whole heck of a lot. It was built by a man and his son. His son was Zacharias, and the guy's name was Hans. And in most books, you don't even see them named. And you got a magnification of about 3 times. Obviously, this could not be used to see microorganisms. You would need way more magnification. And again, you can look at all sorts of other microscopes of different types, just phenomenal, from different countries, including, we'll get to in a second, Leeuwenhoek's handheld one. Okay, here's some of the people involved in the development of the microscope. Leeuwenhoek we'll talk about more in just a minute, but notice Kepler and Galileo. You may have already thought about astronomy related to them, because Kepler was an astronomer, Johann Kepler. And Galileo you think of as kind of a physicist, astronomer. Hooke, Robert Hooke of the 1700s, a biologist. These were people that worked on the development of the microscope. And if you look again at the Museum of Microscopy, you'll realize that there are way more microscopes than you ever thought were developed, of different types and different shapes and things like that. Okay, so we're going to look at 4 of the 5 light microscopes listed here. We're not going to look at confocal, although I'll show you what it looks like when you look at objects in there. Okay. I already showed you Leeuwenhoek's microscope, his little handheld one. Let me go backwards here. Um, the microscopes we're going to be looking at are called compound microscopes because they have two lenses or more. You know that there's a lens in the ocular eyepiece, and at any given time you're looking at one of the lenses of the objective lens, a 10, a 40, a 100, whatever. So your object, the light rays are going through an objective lens and an ocular lens, and that means that this is a compound microscope. Leeuwenhoek's little handheld microscope had only one lens. It was a simple microscope. Okay, so that's simple versus compound. Total magnification, ocular times objective lens. So our microscopes only magnify as high as 1,000. The condenser is the object in a microscope that captures, condenses, focuses the light rays on your object. So if you look over here at the picture at the bottom right, here is your ocular lens right there. Here is your objective lens right here, whatever it is. Here is your specimen on a microscope slide right there, and you want all available light rays coming up into the lens. All available light rays. That's what bright field microscopy is. This max light, although you can control it with your diaphragm to reduce it, the max light gives you a white background with your object being darker against the white background. Now this is the one I've just highlighted is a algal organism, and it's got chlorophyll. It's greenstone stain, but you see a stained specimen of bacteria right over there. And again, a reference to the importance of oil. And here's some stained bacteria. So that's bright field microscopy. That's the one you're familiar with. Also in your microscope, of course, you've got mirrors so that the light rays hit the mirror and then are projected up to your ocular lens in your eye. Okay, here's dark field microscopy. In this case, you want minimal light rays hitting your object. In fact, you want to block them. This has a special condenser. So the condenser is underneath the stage. It's sitting right there. And looking down, if you were looking down on it this way, you know, you take, let's say you take the stage is right there, off, and you're looking down on the condenser, just holding it, you would see that there is a dark paint of black over the condenser. Okay? And the only place where light rays come through are around the edges. Let me change colors. So in blue, these are the only areas where light comes through. So the light comes through at an angle, you see it right here coming through these edges, and hits your object that's on a slide and bounce off and come up into your eyepiece. So your objects, here's a bright field right there, your objects are white on a black background because you're blocking most of the light rays. You might not think this is all that exciting because it's in black and white, but boy, when you start looking at pond water on dark field, it's really fascinating because the white on the black background really enhances your contrast. The magnification is the same and the resolution is the same, but everything looks much more stark and interesting on dark field. It's really good for seeing movement, really good for seeing large objects. Not too wonderful for seeing little tiny bacteria though. But it is interesting. Okay, phase contrast. Microorganisms and cells of any type, or it could be you're looking at caffeine crystals, it doesn't matter. When you put them on a microscope and light goes through these objects, the light goes through the objects at different rates because of refractive properties of the object. So when you shine a light through a cell, you get different light movement through the fluid, and if it hits any organelles or a nucleus, things like that. And then, of course, coming out the other side of the cell, through the cell membrane, and then eventually it's got to hit the lens. So there are a lot of things kind of blocking light rays. So phase microscopes take advantage of this. They use a special condenser that gets the light rays out of sync purposefully, enhancing contrast, hence the term phase contrast. So on the picture you see over here on the right, there's the special condenser right there. Here's actually what the condenser looks like here. And there is a corresponding condenser that goes with it in the objective. And notice that there are two rings right here. They're superimposed. And what that does is it gets the light rays out of sync. Now, this capitalizes on different refractive properties of your object. So take a look down here at the bottom. Over on the left, these are yeast cells. They're large, they're eukaryotic, unstained. You're looking at this on bright field microscopy, all right? You're looking at them on a high power, 100x. All right, you can see them, it's not a problem. Now, look over here at dark field. This is dark field on the far right. And they look much more interesting. Again, the contrast is much greater. You can see some little white things inside of them. You can see a nucleus that's more predominant and so on. Now look in the middle and you see phase contrast of the same thing. Same three objects, three different microscopies. This is phase contrast. Your background is gray. Your objects are different shades of gray, light gray, darker gray, lighter gray. You've got kind of a whitish halo around the cells. The whole thing stands out at you with much greater contrast. And you can really see the nucleus and internal structures. So this is the beauty of phase contrast. I'll show you some comparison pictures in a second. Okay, here's a great one. This is unstained, phase contrast. Your background is kind of grayish. Now this guy's got chlorophyll. He's not been stained, so he's slightly green. And again, you can really see the internal structures. You can see chloroplasts inside of the cells. You can see the cells well delineated. You have a little bit of a halo around the cells. Really great contrast. Okay, here's a comparison of the three that I've mentioned. So this is an epithelial cell from your mouth. The whole thing, the big thing right here, is one epithelial cell. Now you see some little dark things on there. Those are bacteria. Now take a look at dark field, and again it's much more interesting looking. The cell itself doesn't stand out as much, but the bacteria stand up very nicely. Now look at phase contrast, and you really see great delineation. You can even see where like the bends and the corners of the cell are. You can see things that you don't see on the other bright field and dark field. You see some little like areas right in here that didn't even show. And then over on the bottom right is a confocal microscope, which is another type of phase called a Nomarski. And it also shows you great delineation along with a kind of a three-dimensional view. So you see a lot of pictures. You'll see pictures of all different types in your book. But if you were looking at things all day long, you'd probably want phase microscopy. Okay, so let me finish up with fluorescent microscopy. We're still in light microscopes, but there's something very different here, and that is that we are going to use ultraviolet light. Now, we were using white light in the previous three scopes. Remember, the wavelength of light is between 300 and 750, with most of it being in the best view, for us to see anyway, between 500 560. But again, it's all wavelengths added together. In this, though, we are using UV, and remember, UV is a smaller wavelength than visible. It's less than 300. So remember that formula I showed you earlier, 0.61 times wavelength of light divided by numerical aperture. Well, if you make that wavelength of light a smaller number in your numerator, you will get a smaller overall value. And so you get much better resolution because you get a smaller resolving power with fluorescent microscopy because you're using a different wavelength of light. Now, here's the light microscope setup down here. We are using UV light. Now, UV cannot be seen by we don't have receptors for UV light. This is UV light in blue. You see it right there. This is a very different microscope than our scopes. Got a different kind of lamp. Okay, so there's the UV light, and it hits your object. Your object is sitting right here on a slide. And it may be that you used a fluorescent stain called a fluorescein stain to stain your object. And when it gets hit by the UV light, it causes that dye to fluoresce in lots of different colors, like oranges and yellows and reds and chartreuse and light green and all sorts of fluorescein stains. Now, the UV light has been converted with that fluorescein stain to visible light, which you see in pink, and that can be seen by your eyes. In addition, some microorganisms and some organisms have a natural fluorescent. They may have their own chemicals inside their bodies that fluoresce when hit with UV. And you can pick those up with a fluorescent microscope. And fluorescent microscopes are very often used in immunological tests using dyes of different types also. Okay, so let me show you. Okay, I'll show you some variations of this in lecture. I'm going to stop here. We'll finish up electron microscopy and the rest of this chapter in the next video capture.